Welcome you all for a new video where we're going to solve problems related to the carrier concentration, compensation, doping and charge neutrality concepts. The first part of the same video was about the review of all these concepts. The video link is given in the description box. You can just have a look into it before we proceed with the second part of this video. The first problem says that we need to estimate the donor concentration in a compensated silicon-based semiconductor at 300 Kelvin if EC minus EF, where EC is the conduction band energy level and EF is the Fermi energy level, and the difference between them is 0.2 electron volt. And the next parameter that is given is the density of states in the conduction band. That is why it is given as N suffix C, which is equivalent to 2.8 into 10 to the power 19 per centimeter cube. And the accepted doping concentration is 3.3 into 10 to the power 16 per centimeter cube. So now we need to determine the whole concentration also. First, to estimate the donor concentration, we have an understanding that the number of electrons, the total number of electrons in an n-type semiconductor is contributed mostly by the donor doping concentration. So this is how we write, and we usually relate N is equal to NC exponential of EF minus EC by KT. The reason why I have specifically chosen this formula is we are given with the effective density of states in the conduction band. So since we know this NC, I'm just relating with the electron concentration with this formula. But what is given very specifically in our problem statement is we need to identify the donor concentration for a compensated semiconductor. So we know for a compensated semiconductor, equal amount of opposite type of impurities will also be present. So which means along with donor impurities, acceptor impurities will also be present. Then what about the electron concentration equation? The electron concentration becomes Nd minus Na. So this will be the net doping concentration. So now we need to relate this formula along with this effective density of states inclusion of formula, and then we'll be able to identify what is the donor concentration. Now the final equation for estimating the donor concentration becomes like this, and here we need to note down that all these energy levels are given in electron volt. So just to have a conversion unit, I have just divide this KT by 1 electronic charge, which is 1.6 into 10 to the power minus 19. Usually in the formulas itself, they start giving it like this with a multiplication of Q here, because KT by Q, if you write this, Q will be in the numerator section. So this is just the unit conversion. Now all the values are given. Just straight away substitute the values in this particular equation, and then we will be able to identify what is this donor doping concentration. Now after substituting all the values in the ND equation, we have got the final ND answer as 4.5 into 10 to the power 16, because the EC minus EF was given, but here the equation has EF minus EC, so therefore I have just taken minus of 0.2. All other details as per the problem statement I have just substituted. And then we need to identify also what is the hole concentration, and we know how hole concentration and electron concentration are related with the Morse action law. So therefore I need to first identify what is electron concentration. So for that, since it is a compensated semiconductor, we know that N is the net doping concentration, which is Nd minus Na, because it is involved with both the type of impurities in the compensated semiconductor. So I've just taken the difference between Nd and Na. So that gives us the electron concentration, and Ni, which is the intrinsic carrier concentration for the silicon, which is a constant value, which I have taken as 1.5 into 10 to the power 10. This will not be specified in the problem statement, so because it's a constant. So just take that and use the mass action law to determine what is the hole concentration also. The second problem statement is about a p-type silicon material which is compensated to maintain charge neutrality at room temperature is being given, along with the acceptor impurity doping concentration of 2.5 into 10 to the power 19 per centimeter cube, and donor doping concentration is also given with 5 into 10 to the power 17 per centimeter cube, because it is a compensated semiconductor, so it involves both the type of impurities. And what we need to determine is the majority hole and minority electron concentration without compensation. So first we don't have to understand about the compensation, and it is very specifically given that it is a p-type silicon material. So with that p-type silicon material, majority will be the hole charge carriers and minority will be the electron concentration. So without compensation, we can just use mass action law to find out these concentrations. The second one that we need to identify is the net positive charge after ionization. So this we need to be very careful because we know about the charge neutrality concept. So with that, we can identify what is a net positive charge. And then finally, we need to identify the conductivity when the mobility of holes is given as 450 centimeter square per volt second. The first one we need to identify is the majority hole and the minority electron in a p-type silicon material without compensation. So the formula will go actually like this, because without compensation for a p-type silicon material, the majority charge carriers are contributed only by the accepted doping concentration, and that is given in the problem statement, which is 2.5 into 10 to the power 19 per centimeter cube. This is without compensation. So similarly, we need to identify the minority electron in the same p-type silicon material. So that can be obtained from mass action law, which relates Ni square by Na. So this also we know, Ni, which is for a silicon material, it is a constant, which is 1.5 into 10 to the power 10, the whole square divided by 2.5 into 10 to the power 19. Which is equivalent to 9 per centimeter cube. And this is the notation for finding out the minority electron. So the first letter denotes the electron concentration. So it is N. And this is going to be minority in a p-type semiconductor. So the suffix is always denoting the type of semiconducting material that we are choosing. And the second part was to determine the net positive charge after all the impurities got ionized. And this is also with respect to the charge neutrality concept, where we have understood what is the net positive charge from the equation, which is P plus Nd plus. So from the first part of this problem, we have identified what is the whole concentration, and the donor doping concentration is also given for us. So just add both of them. That will give us 2.55 into 10 to the power 19 per centimeter cube. So coming to the last part of this particular problem, where we need to identify what is the conductivity for the p-type semiconducting material without compensation. First I have taken the formula because it is without compensation, just the whole concentration is enough to identify what is the conductivity in a p-type semiconducting material. This is the whole concentration, electronic charge, and this is the mobility of holes, which is given in the problem statement. And this gives us the conductivity in a p-type semiconductor, which is 18 per ohm per meter. Now, since the statement was given in terms of compensated semiconductor, I would like to rewrite this same equation in terms of compensated semiconductor in a p-type material. Now, the final equation of conductivity of a p-type material, which is having both the type of impurities. So then in such a case of a p-type material balancing both the type of impurities, the net doping concentration will be Na minus Nd, because it is of a p-type material. So if it is n-type material, we used to write it as Nd minus Na, since it is given here very specifically as a p-type material, and along with that we have a compensation, and therefore the statement goes with Na minus Nd into Q into mu p. So all other things the same. We know both the type of impurity concentration values. Just substitute and find out what is the conductivity of a p-type material, which is inclusive of the compensation process. So the last problem that we are going to solve in this particular video is about a sample of intrinsic germanium at 300 Kelvin is considered to have a resistivity of 50 ohm centimeter. The germanium sample is uniformly doped to the extent of 5 into 10 to the power 14 phosphorus atoms per centimeter cube and 10 to the power 15 gallium atoms per centimeter cube. So assume that the mobility of electrons and the mobility of holes are given, and we need to estimate what is the intrinsic carrier concentration, electron concentration, hole concentrations, assuming all the impurities are completely ionized. So therefore, we need to bring the concept of charge neutrality, where all the impurities are completely ionized. So that will give us what is the electron and the hole concentration. Finally, we will try to use the mass action law also. Now we need to identify first what is the intrinsic carrier concentration. But let us understand what are the values that are given for us in the problem statement. So there was a statement where we had the data of resistivity. So I just got to strike about the formula which relates intrinsic carrier concentration with the conductivity, and we are very sure that the conductivity and resistivity are inversely proportional to each other. So therefore, by just relating the intrinsic carrier concentration and the conductivity formula, I can just find out what is my intrinsic carrier concentration. So I have just replaced sigma I as 1 by rho. Q we know, mu and mu p is given as 3700 and 1500. So both we can add together, and I've just substituted the values to get the intrinsic carrier concentration of a germanium sample as 2.4 into 10 to the power 13 per centimeter cube. Next, we need to identify the electron and hole concentration, assuming all the impurities are ionized. So I have just taken the charge neutrality equation, which relates P naught minus N naught equal to Na minus Nd. Since only the values of Na and Nd are known, we have to identify what is N naught. Again, that if we replace in terms of P naught, so therefore we get to know about the mass action law, where we can replace this N naught as Ni square by P naught. So therefore this equation entirely becomes a quadratic equation. So that let us see how it is getting changed after finding out the values of Na minus Nd and after substituting for N naught as Ni square by P naught. Also understand the problem statement does not give us these values directly. Indirectly, it was given as 5 into 10 to the power 14 phosphorus atoms per centimeter cube, and the germanium sample was also doped with 10 to the power 15 gallium atoms per centimeter cube. So with this, we have to identify ourselves which is going to contribute to the donor doping concentration and acceptor doping concentration, as we are very well aware that gallium atoms are falling under the category of acceptor doping concentration. I have just categorized Na equal to 10 to the power 15 per centimeter cube, and we know phosphorus is a donor level impurity. So therefore, the donor doping concentration value has been taken as 5 into 10 to the power 14 per centimeter cube. Now we have to just directly substitute this here and find out the difference between Na and Nd. Now the final value of Na minus Nd will be 5 into 10 to the power 14 per centimeter cube, and N naught can be replaced as Ni square by P naught in the same equation. After bringing all the terms towards the left-hand side, this looks like a quadratic equation which is similar to ax squared plus bx plus c equal to 0. And we know how to solve the quadratic equation, and the solution can be given in the form of x equal to minus b plus or minus square root of b squared minus 4ac by 2a. Maybe you will get two values. We can just go with the positive value, and P naught, the final value that we need to identify, is the whole concentration. So that can be solved by substituting what is Na minus Nd, that is also available in our hand, and Ni, which we have identified in the first part of this same problem. And after substituting all these things, we get what is the value of P naught. And the final value of P naught is 5 into 10 to the power 14 per centimeter cube. And this can be extended further with the mass action law to identify what is the electron concentration from the mass action law by substituting the intrinsic carrier concentration obtained from the first part of this problem, and P naught we have just identified as 5 into 10 to the power 14. So with that, we can identify what is N naught, which is 1.152 into 10 to the power 12 per centimeter cube. The same problem can be extended if an applied electric field is given, and if current density has been asked to identify, we can just go with J is equal to sigma E, and where sigma is here, we have two different types of concentration. So therefore, the conductivity will now take a different form in terms of sigma is equal to N naught mu N plus P naught mu P into Q. And using this conductivity equation, which involves both the type of charge carriers, then if the applied electric field is given, we can always find out what is the drift current density. Hope you all have got some interest towards the problem solving approach of the charge concentration, intrinsic carrier concentration, estimating the hole and the electron concentration based on the charge neutrality concept. And a highlight of our video was about the compensation process. That compensation doping has helped us to understand how to estimate the different carrier concentration profiles. Meet you all in another interesting video of problem solving approach of different topic. Until then, stay safe. Thank you all for watching this video through Electronics Insight channel.